So this last part of chapter 17 is about complex ions. So transition metal ions are often good Lewis acids. Remember, Lewis acid is an electron acceptor. Yeah, I know you don't remember that. I'm just trying to... Lewis acids are electron acceptors. Lewis bases are electron donors. So water molecules can act as Lewis bases. So this is, we look at the Lewis structure for water, and we see that oxygen has two lone pairs. It's those lone pairs that are the donated electrons. So silver ions are actually hydrated when they're in solution. So you've got a silver ion and it has two water molecules attached to it. This is not an ionic compound, this is an ion itself. And so there is still an overall +1 charge. Just like hydrogen ion doesn't actually exist in solution, silver ion doesn't actually exist as a bare ion either. It forms this complex ion with water. A complex ion has a central metal ion that has one or more ligands bonded to it. Okay? The ligand can be a neutral molecule, it can be an ion, and those ligands act as Lewis bases. So they've got lone pairs that they donate to that central metal ion. So we've got the metal ion in the middle, and the things that attach to it are called the ligands. So these complex ions form, and as you might have guessed, because they're in this chapter, they form equilibria. So if we have a stronger Lewis base that's added, it can displace the weaker Lewis base in the complex ion. So remember that water is amphoteric, and so water can act as an acid or a base, and it's not a strong acid or a strong base, it's weak in both cases. Ammonia is also a weak base, but it's stronger than water. If we look at the Lewis structure for ammonia, we again see that lone pair of electrons, and that's what allows ammonia to be a Lewis base. It can donate electrons. So these ammonia molecules can displace the water molecules in the complex ion, and that is an equilibrium. So to make things simpler, we typically just leave the water out of it, because all of these are in aqueous solution. There's always water there. The water being a pure liquid in here, its concentration doesn't come into anything. And so the silver ion is a lot like the hydrogen ion, which we understand to not be out by itself, but we don't need to always specify what it's attached to. It's just that silver needs two babysitters instead of one. So we can write it like this: the silver plus the ammonia forming this complex ion, and now we have an equilibrium constant, and these are called Kf. These are the formation constants. It's the constant for the formation of the complex ion. It's calculated in the same way as all the other equilibrium constants. The concentration of the products over the concentrations of the reactants, and if there's a coefficient, that becomes the exponent. Okay? So here's a table from your textbook listing formation constants for a bunch of complex ions. And you can kind of see why they're called complex ions, because they're kind of complicated, right? So let's look at an example here. You mix a 125 milliliter sample of a solution that's 0.0117 molar in nickel chloride with a 175 milliliter sample of a solution that is 0.250 molar in ammonia. After the solution reaches equilibrium, what concentration of nickel 2 remains Kf is 2 times 10 to the 8th for that nickel ammonia complex. Well, a good place to start is by writing out the equation, chemical equation. So we can look at this as nickel ion plus ammonia and that's going to be in equilibrium with that complex ion, and they're giving us the formula here. It's 6 ammonia molecules, and overall that still has a 2+ charge, and that also is aqueous. So then we need to balance this equation, and we need 6 ammonia molecules. Then we're going to look at what do we have in our mixture here. So we've got 2 different solutions being mixed. We're going to need molarities for the Kf calculation. So we've got 125 milliliters of 0.0117 molar of the nickel. So that gives me 1.4625 millimoles of the nickel ion. And then we've got 175 milliliters of 0.250 molar ammonia. So 175 times 0.25, 43.75 millimoles of ammonia. That formation constant, is this reaction favoring products or reactants? Products. 10 to the 8th is a big number. That would make an awesome salary, wouldn't it? 2 times 10 to the 8th dollars per year? I could go for that. So is there going to be very much free nickel in this solution? No, there isn't. So we can do a similar thing that we did when we were looking at equivalence point and after titration calculations. And we can say, well, how are these things going to react? Let's just assume that's going to go all the way to the products, and then we'll see how the equilibrium shifts back a little bit. Because if we do this in the forward direction, we're going to have the same issue we had with that first written problem on the exam, where the problem solver is going to freak out on you and say you can't do that. So we have the millimole amounts for the Kf calculation. We need that to be in molarity. So we need to find out what the total volume of the solution is. So that's 125 plus 175, which is 300 milliliters. So to find the molarity of each of these substances, we take the millimoles divided by the milliliters, and then we get molarity. So 1.4625 divided by 300. The nickel is 0.004875 molar. And the ammonia, 43.75 divided by 300 is 0.1458. Before any reaction occurs, those are the molarities of our 2 reactants. Now, because this is so large, we are going to assume complete reaction, push it all the way to the products, and then work the equilibrium back. So this is going to lose x, and this is going to lose 6x. Over here, we're going to gain x. Now, if this is reacting completely, we have to consider which of these reactants is limiting. It's not necessarily obvious because there's a 6-to-1 stoichiometry here. But if I take this concentration of ammonia and divide by 6, I get 0.024, which is greater than this number. So nickel's the limiting reactant. So we're going to lose all of the nickel. So X is going to be equal to the molarity of the nickel. So this is minus 0.004875. This one is minus 6 times 0.004875. And over here, this one is plus 4875. So we're going to start with 0 of that. And the ammonia, is going to be 0.11655. And then this one's going to be, that was 0.004875. So any questions about what I did there? When we solve for x in an equilibrium constant expression, we need the x to be a small number, because when the equilibrium changes, we're subtracting x from something. And if we're subtracting a relatively large x from a relatively large number, things go crazy very easily. That's the mathematical term for it. So this is what we're going to call our initial concentration. Then we're going to look at the change and the equilibrium. So we've reacted all the nickel, so now the reaction has to come back towards the products, right? Because it can't go any further in the other direction. So this is going to be plus x, and this is going to be plus 6x. And this is going to be minus x. So we've got x, and we've got 0.11655. I've got too many digits in there, but so 2.0 times 10 to the 8th is equal to the product divided by the reactant concentrations and very important not to overlook the 6 here. This is raised to the 6th power. Everybody okay with that? Now, if this is 2 to the 8th, 2 times 10 to the 8th, and it's coming back this way, do we expect x to be a large number or a small number? We expect it to be a small number. And unlike the some of the acid calculations where doing x is small didn't really make anything simpler, here doing x is small makes this much simpler, right? So let's try x is small, then we just disregard this minus x and the plus 6x, and we're going to say, well, this then would be approximately equal to 0.004875 divided by x times 0.11655 to the 6th power. So then x is going to be 0.004875 divided by 11655 to the 6th power and divided by 2 times 10 to the 8th. That just seems wrong, doesn't it? Anybody else get that? It doesn't seem possible that you could get the same number out of that. Does that bother anybody else? I'm gonna try that again. Yeah, I thought that was just not even possible. Okay, I don't know how I ended up with that number, but second time, I do not get that number. Now I forgot what I counted to. 6? 6 minus 6. Anybody else get that? Okay, I got a nod at least. So, is that small relative to these numbers? Yeah, it is. I mean, we could divide it and find out the percentage, but I guarantee you it's less than 5%. So, we're asked what is the concentration of nickel, and the concentration of nickel is X, and so this is our answer. Question?
Yeah, so you got rid of the 6x in the denominator because the x is small.
Yes. Yeah, so I got rid of, I'll just highlight those. I got rid of this and this because the x is small approximation says, well, x is so small that when we add it to this other number, it's not even going to make a difference. Even multiplied by 6. Yeah. And you can do x is small, and then you always have to check and make sure that's true. And so we can show ourselves that that's true by taking that result, multiply by 6, divide by the 0.11655, multiply by 100, and it's 0.05%. So then x is small. Any other questions? So these calculations are a little bit different because most of these formation constants are very large numbers. And so then what we have to do is we have to push the reaction all the way to the product side and then solve the equilibrium going backwards. Okay? So I sprung that on you on the first exam to see if anybody would figure it out. Nobody did. That's okay. Now I'm teaching you how to do it, so there definitely will be need for this in the future. Okay? So complex ions have an effect on solubility. So the solubility of an ionic compound containing a metal cation that forms complex ions increases in the presence of Lewis bases that complex with the cation. The most common Lewis bases are ammonia that we've looked at, cyanide, and hydroxide. These are the ones that often increase solubility. So over here we have silver chloride solution. This is obviously saturated, And we've looked at that and how that dissolves, right? And there's a KSP involved. Let me write that down here. So when we look at solubility, we've got silver chloride solid in equilibrium with silver ions and chloride ions. When we throw ammonia in there, ammonia forms a complex ion with the silver. That means that the silver is no longer available to precipitate with the chlorine. So in terms of thinking about Le Chatelier's principle, complexing this ion essentially reduces its concentration and causes more of the solid to dissolve. So we've got pictures and illustrations. So here we've got ammonia and water. We've got the silver chloride. And the ammonia, come on, pointer. The ammonia is going to complex those silver ions. And so much more of it will dissolve than in pure water. It actually changes the equilibrium constant by a factor of 17 million. That's pretty big. We can look at it this way, the two equations. So here we've got KSP, the silver chloride dissolving. KSP for that is 10 to the minus 10. Here we've got the silver forming a complex ion with ammonia. The formation constant there is 1.7 times 10 to the 7. And if we add these two equations together, we get this overall equation. And when we add equations, we multiply the equilibrium constants. So we've got KSP times KF. So now we get 3 times 10 to the minus third, which doesn't seem all that big, but it is, because we've increased it by the factor of this KF 17 million. Any questions? Yes?
How do you know if they're going to form a complex ion?
That's an excellent question. How do you know if they're going to form a complex ion? Look in the table and see if it's there. Yeah, pretty much. I don't know which ones, off the top of my head, I don't know which ones form complex ions or what the complex ion looks like. Doing problems like this, you're going to need to look up the KF anyway, and so it's going to show you what the complex ion is. So if we go back to this table, pointer. Here we've got the silver with ammonia, and there's the KF. And we can also see that silver forms a complex ion with cyanide and with thiosulfate. So we just need to look at this and see, do the things that are in there form a complex ion? And you do that just by looking at the table. That's not a very fancy answer. So many metal hydroxides are insoluble or only very slightly soluble in pure water, pH neutral water. We're talking things like calcium hydroxide, magnesium hydroxide, iron hydroxide. In our solubility rules table, hydroxides were generally insoluble except for the alkali metals and ammonium. But metal hydroxides are more soluble in acidic solutions. And that's because as you add the acid, you're removing the hydroxide, and that's going to push the equilibrium more towards the products and cause them to dissolve more. Some metal hydroxides are amphoteric and can also act as acids. And so for these guys, they also have increased solubility in basic solutions. And aluminum is our prime example of this. Aluminum is just weird. So here we've got aluminum that can form a complex, well, no, this isn't a complex ion. That is aluminum hydroxide, right? There's no charge on that. If we add hydroxide to that, it can form a complex ion. That complex ion, being an ion, is going to be soluble. The more hydroxide you have, the more of this will dissolve by forming this complex ion. So at high pH, it will be more soluble. At a low pH, it's also more soluble. Because just looking at this dissolving, this is our equilibrium, right? And so 3 hydroxides here. In acidic solution, these are going to react with water. We reduce this concentration, that increases the solubility. That's the common ion effect. So in our separation that we're doing in lab, if you look closely at what's going on when you test for aluminum, aluminum gets precipitated and dissolved again, and then precipitated again. And aluminum's one you have to be careful with, because if you don't hit it in the middle, it is soluble at low pH and at high pH, and not at neutral pH. So aluminum ion in solution is inherently acidic. It's that and iron 3 are those 2 small, highly charged cations that connect as acids. So aluminum can form a complex ion with water, and then if in the presence of more water, which of course is there, this complex ion can lose a hydrogen ion from one of its water ligands. So here we've got 6 water molecules, right? It's a little hard to look at. Here we've got 5 water molecules and a hydroxide. And the water here went to hydronium ion. So this complex ion donated a proton, a hydrogen ion, to the water molecule. And when it does that, one of these water molecule ligands becomes an OH minus. And that, of course, changes the charge here. But that's aluminum acting as an acid. If we add base to this solution, we're going to be removing these hydronium ions, and we'll drive this reaction more towards the right, towards the products. And then we can actually remove more protons from more of those water ligands. So here we've got 5 water molecules, and now we've got 4 and 2 hydroxides. And here we've got the 4 water molecules, 2 hydroxides, and we can remove another proton. So we've got now 3 hydroxides and 3 water molecules. At this point, this is no longer an ion, because the 3 OH minuses, -3 charge with the +3 charge on the aluminum, this isn't an ion anymore, and it will precipitate. You get that? It's kind of weird. So this is acidic in solution. As we add base, we can cause the aluminum to precipitate, and then if we add more base, we can dissolve that and form this complex ion that's now negative. I didn't invent this to torture you. It's just a weird thing that aluminum does. So here we have pictures. So in acidic solution, we have this complex ion of aluminum where it's got 6 water molecules as ligands. That will be soluble. pH neutral solution. Now we're going to have this solid, or the AlOH3, aluminum hydroxide. I kind of skipped over something down here. This AlH2O3 OH3 solid is equivalent to AlOH3 solid because, well, just because it is. If we take that solid and we add more hydroxide, then we can get this soluble complex ion. It's got hydroxides, it's now a negative ion. So cations that can do this, aluminum of course, chromium 3, zinc 2, lead 2, and tin 2. And the extent to which it will dissolve in both acidic and basic solutions depends on how amphoteric that complex is.